Problem 2 is a little trickier, but not by much. We just have to be aware of what each of these statements means in terms of probability. So we have weather being either good or bad. We have time of day being either morning or rest of the day, and we're looking for delays at an airport. So we're being told that in the morning there's no delay if there is good weather. So essentially what that means is that probability of delay, given that it's morning and good weather, that is 0. But bad weather causes half the flights to be delayed. So similarly, we have delay given that it's morning and bad weather. That is a 0.5 probability. Then if we move to the next one is for the rest of the day, chances of delay during good and bad weather are 30% and 90%. So we do the same thing as before. So delay given rest of the day and good weather, we've got 0.3, and delay but rest of the day and bad weather, that's 0.9. 30% of flights leave in the morning, 70% of the flights leave the rest of the day. That tells us that probability of morning 0.3, probability of rest of the day 0.7. Bad weather is more likely in the morning, but only 10% chance for bad weather the rest of the day. That tells us that bad weather in the morning 0.2, bad weather the rest of the day, that's 0.1. Only two kinds of weather, good and bad, which what this tells us, essentially we can take the complement of these and we can get the good weather for morning or the rest of the day. So that's that information. So we're trying now to find what is the probability that a given flight will be delayed. So we're looking at event D. And let's try to open up a new page here. Let's see how we can do this. Oh, let's just open up a new note. There we go. Okay. So for the first one, finding the probability that there is a delay. So we're looking for this probability, and based on the fact that we are given a set of mutually exclusive and mutually exhaustive events, and those would be, so we could either have morning and bad weather, morning and good weather, rest of the day and bad weather, rest of the day and good weather. So essentially we end up with 4 possible events that cover the entire sample space. So we're going to look to find the conditional probabilities of delay based on these and utilize them in the total probability theorem. So for that, we start with probability of delay. So let's start out with good weather and morning. So we've got the probability of delay given good weather. Good weather and morning, and this we have to multiply it by the probability of having good weather in morning, and then we're going to take the probability of delay given bad weather and morning, probability of bad weather and morning, and add the probability of delay for good weather rest of the day, good weather rest of the day, delay bad weather rest of the day. Okay. All right, so now probability of delay, if the weather is good and it's the morning, we know that that is 0. And then we multiply that by the probability of good weather and morning. Now, these intersection probabilities we can express as good weather in given the morning and then probability of morning. Same thing with these, we can do the same thing because again, we look at what we know. We know the morning flights are 30%, we know what's the probability of good weather during the morning. So again, we're trying to express everything based on things we know. So good weather in the morning, that will be 1 minus 0.2 because we're using, again, complement of the bad weather in the morning, which was 20%. And then we have the 0.3 probability of morning flights. Okay, so now let's go to the second set of terms. And those would be 0.5 times 0.2 times 0.3 again. And now we knocked out morning for both good weather and bad weather. All right, and then we've got 0.3 for a delay with good weather and the rest of the day. Again, we take the complement of from the bad weather rest of the day, and then we have 0.7 for the flights in the rest of the day, and finally we have 90% times 0.1 times 0.7. So really just a matter of utilizing the total probability theorem, identifying the mutually exclusive and exhaustive events, and just expressing everything based on things we know. So if we just perform the calculation, we'll find the probabilities of 0.282. Now for the second part of the problem, we were being asked, and let's switch back to that node here. Let's see. Let's go here. So let's go back to the midterm. So the second one is, if the flight is delayed, what is the probability that it is caused by bad weather? So with this one, let's go here. So this is B. So we're looking for the probability of bad weather given delay. And the first thing to realize is that if we have a delay, there's only two chances for bad weather, so which are mutually exclusive. So we can either have bad weather and morning, so given delay, or bad weather and rest of the day, given the delay. Now we can express these from the definition of the conditional probability. So now we're looking for the intersection of all three. So we've got B, bad weather, morning, and delay, divided by probability of delay, which we have calculated, plus the probability of bad weather and the rest of the day and delay. The reason we can do it like this is that, and you could have used the Bayes theorem as well for this, but we can do it this way, essentially doing the same thing. But the reason we can do this is because we can now express delay given bad weather and morning, which we know what it is, and then we can just use the probability of bad weather and morning, which we could express as same as before. And then we have the probability of delay given bad weather and rest of the day. So we have bad weather, rest of the day, rest of the day. Now here we know everything. So we've got 0.5 times 0.2 times 0.3 divided by 0.282. So it's just a matter of perform the calculations and getting 0.330 for the probability.